Hello and welcome back to Statistics 1, section 3.2, measures of variation. So last time we did measures of the center. We did mean, median, mode. We said that we can look at mean, median, mode for sample and for population. If population is reasonably small, like let's say all of the students of this class, I forgot the section again, it's 90. Thank you. Then you guys are population, and it's very easy to pool, in the classroom where it's, such a small size. But think of the population of United States, think of the population of the world, think of the number of ants, right? I don't know what you survey the ants, but still. Certain population size cannot be easily surveyed, so we have sample, and because we have sample, then we have sample mean and sample everything else. So today we are going to talk about measures of variation, and we are going to have sample standard deviation and population standard deviation. We started talking about the variance. So before we get into these standard deviations and so on, we'll first talk about something that is called the range. So the range of the data set range is, I'll see you next week. So range is max minus the min. So this is, so max is the highest value observation. And min is the lowest, smallest value observation. We know that observation is a single measurement. So if I am to ask you guys, well, I'm not supposed to ask about age, right, because we have ladies, but I can ask about the weight. If I'm to pull the weight, right, then we're going to have the lightest, and we're going to have the heaviest in the classroom, right? So those are your min and max, and then the range is a simple difference of the two numbers. Max minus min. So I'm just going to make up sample data. So made up sample data. And I'm just going to, put a whole bunch of numbers. So let's go 13, 19, 19, 27, 31, 33, 49, 51, 52, and 53. Nice. One more. 53 and what else? 62. All right, fine. Thank you. Great. So now, looking at this made-up data, this is not data of anything. I mean, this could be ages in an extended family or something. But then, whatever, doesn't matter. So it's made-up data for something, and it's important to know that the first number is the min, and the last number is the max. So if you're calculating the range for this data, it will be 62 minus 13, which gives us, very good, 49. So that's the range. And we are now moving to the next concept because there's nothing else there. The next concept is the sample standard deviation. So sample standard deviation. We would like to look at the variance of data in respect to the mean value of the data set. I want to know the variance in data because I can see it's descriptive statistics, right? So I can see what the data set is like in terms of variance. We talked about those basketball players where both teams had the same mean height, but then one team had a very tall and very short player who averaged to be just the average height of the other team. And we said that very tall player in basketball and very short player in basketball have their strengths and advantages over the medium range players. Short guys should be very fast, quick to turn, and zoom around the field, and the very tall guy is just going to tower everything, and we know how important jumping and reaching high in basketball is. So having those two average into the other two guys that are mid-range, that will be moving slower than the short guy and jumping lower than the tall guy, clearly are at disadvantage. Now you can see that the mean doesn't really tell us that the whole thing is fair. So here are so let's say these are the basketball players, clearly. So these are the two mid guys, right? And then the other team has the shorter guy and the taller guy. So now you can see that the average over here, which is the line that I'm drawing now, right? The mean might be, let's say, 6. So mean for both, let's say it's 6.3, whatever, right? But then if this guy over here is 7.3, well, that's right. Then that's an issue for 6 feet 3 inches. So 6 feet 3 inches. Yeah. So let's say that's the case, right? So clearly there is advantage on the right in this case. Now you can also think about the distribution of wealth or whatever, where you have a neighborhood where every house makes pretty much the same income, and then a neighborhood where you have low income and someone who's excessively rich in the same neighborhood. So there are ways. Now when you look at the mean, right, you don't see those discrepancies. But if you look at the variance, you definitely see those discrepancies. So that's what the standard deviation is going to measure. These types of variation in respect to the mean. So you will see that the mid guys will have a very small standard deviation because they are at the mean, where the very tall guy and the very short guy will have larger deviation variance from the mean. And that's what we are measuring today. So we already talked about the sum, and this is going to be the sum calculation. We are going to create a chart to try and get through the formula quickly. So here is the formula. Again, don't panic, lock the doors. Sample standard deviation is the square root of the sum of xi minus the mean squared divided by, right on time, see? As I'm writing these really cool things. So this over here is known as the sample standard deviation. You have the summation, same thing that we talked about, the mean. So you compute each individual one, then you add them all up, and then you divide by n minus 1. N is the sample size. So now, as for the legend, to understand what these letters mean, so S is the sample standard deviation. Lowercase n is the sample size. Xi, individual observations. X bar sample mean, which, if you remember, was sum of xi divided by n, if you recall the last class. And that's it. So we know what each one of these letters mean. So now what we are going to do is compute standard deviation for the data set that we have from before. So this is my made-up data set. And I'm going to compute the standard deviation for it. The way I'm going to do this is I'm going to create a chart of that. Yes. So if you look at the formula, you see that you are supposed to compute the mean first, because you need the mean. You will be subtracting mean from each of the individual entries. So we have to compute mean first. And then we will devise the rest of the chart. So let's go compute the mean. X bar is going to be sum of all observations divided by 11 observations that we have. So I have 11 observations, and what we do is we add them all up. Now, for that, take the abacus and add them. So to find mean, we add all of the values and divide by 11. And we can round to 1 decimal place because there is no decimals in our data at all. So, you know, it will be pointless to put 16 decimals there, precision, where your data does not have even the decimal precision. So I would say 37.2 on the mean. All right, so now I'm just going to write the standard deviation formula on the side over here so that we can deal with all of these things. So I'm going to create a chart. The first column are xi's. Those are individual observations, and you have them in a chart. So that's 13 and 19 and another 19, 27, 31, 33, 49, 51, 52, 53. Who picked this many? 62. There we go. Now, you know PEMDAS. PEMDAS states that you have to do parentheses first, then exponents, then by whatever is the way it goes. So take a look. Parentheses have this subtraction inside. So the first piece that we are computing is inside parentheses. So the next column should be xi minus x bar, which is the mean when we subtract. So xi minus x bar is the next column. So what that means is that you are going xi minus 37.2. So that's what's happening in that column. And then we are going to square those values.
Xi minus 37.2.
Yes. And that's technically all we need in a chart. Because there is going to be a grand total at the end. All right, so we are going to subtract 37.2 from each one of these values. So you go 13 minus 37.2, which is negative 24.2. And then you go 19 minus 37.2, so that has to be negative what? 18.2, another negative 18.2, and then negative 37, that's negative 10.2. Negative 6.2, negative 3 point, no, not 3, 4. And then we are going into 49 minus this, so now that's going to be 11.8. So that's positive, right? 11.8. And then 13.8, 14.8, 15.8, and 24.8. So this column here is the raw data. This over here is data minus the mean. Data minus mean. And now the last column will be squaring each one of the values from before. So we have, now square will kill all the negatives, so you don't have to worry about typing in negative 24.2. 24.2 squared. And again, keep one decimal because our data had no decimal, so you just go one extra decimal. So that's going to be 585.6. Then you have 18.2 squared, which is 331.2. And the next one is the same. 10.2 squared is 104. 6.2 squared is 38.4. 4.2 squared, 17.6, 11.8 squared is 139.2, 13.8 squared, 190.4, 14.8 squared is 219. It's 219.04, but yeah. 15.8 squared is 249.6. That's 3 meals right there. I mean, when you donate to them. 24.8 squared is 615. What have we achieved so far? If you're looking at the formula, the first column is listing all of the values given in the data. The second column is computing the value of the parenthesis. And the third column is computing the value of the entire expression, xi minus x bar squared. Next step is to add them all up. So you will take the third column and you will add all of the numbers to come up with a large number here. Then you will divide that by 10 and take the square root. So now we take the calculator and we type in the 11 numbers to add them up. So 585.6. Did you get 2,821? 2,821.2. Yes. So summation is going to be 2,821.2. So I have 4 confirmation on that one. Please, everyone, you got it? That's 5th. Okay, thank you. So I have 5 confirmations, 6. All right. Okay, so let me write what I have so far. What I have is S equals square root of 2,821.2 divided by 11 minus 1, which is 10. This is what I have. So the entire numerator, you know that symbol, the sigma symbol, means add everything that you have. And that's the reason why we added the whole column here. Right? So xi is each individual one. This is x1, x2, x3, x4, x5, right? We talked about the little counter I, x index 1, right? So x1, x2, x3, x4, that corresponds to individual data points. So we list them all, we subtract the mean, we square the number, and then we created that piece. Then we add them all, and then we have the whole numerator. Now we are going to divide by 10, which is just going to move the decimal, right? So S equals square root of 2,821.2 divided by 10, and S equals the square root of 282.12. Because when you divide by 10, you just move the decimal by 1 place. And now you take the abacus and figure out the square root of 282.12. which gives you 16.8. So standard deviation is 16.8 for this data set. Again, I didn't give the meaning to the data set. I just said, here is some data and the numbers. Again, whether these are going to be ages or weights or shoe sizes or lengths of the shoelaces or whatever, heights, the number of trees in little patches of wood, I don't care what these numbers are, right? We are learning the mechanic of figuring out sample standard deviation. So sample standard deviation is 16.8. And now it's time for us to arrange that 16.8 in your on the graph to see what would that mean. So here's the number line with all of your x's, and we know that there is a mean of 37.2. So I'm going to say 10 let's try 20, 1, 2, 3, 4, 30, 1, 2, 3, 4, 40, it's not gonna fit obviously, 1, 2, 3, 4, 50, 1, 2, 3, 4, 60. There we go. Now move it this way. So what do I have? I have the mean at 37.2. So this is 35, 37.2 should be somewhere over here. This would be mean. Now what I'm going to do is I'm going to compute first, second, and third standard deviation away from the mean. First standard deviation is going to be 37.2 plus minus 16.8. So we're going to get two numbers there, right? And I will show exactly what that entails later. So 37 and 16, that's what? That's 50, 53, 54. 54 if you add them. So that will be here, 54. And then if you subtract 37 minus 16, so that's 36, so that's 20.4. Well, that's here. This over here is the first standard deviation. Now, to find the second standard deviation, you will take 54 and you will add 16.8 to give you 70.8. 70.8 is out there. And that creates second standard deviation. Oh, actually, wait. This goes here. And you are going to have, obviously, second standard deviation here. We only need 3 standard deviations because 99.99% of the data is always in the first 3 standard deviations to the left and right of the mean. Yes? Oh, these are calculations, sure. So, to figure out the standard deviations, you put the mean, and then you add the standard deviation to the mean, and then subtract standard deviation from the mean. That gives you the first standard deviation to the left and to the right of the mean. And then you take 54, add standard deviation, and then take 20.4 and subtract standard deviation to find the second one, right? Because you need to go more to the left. So 20.4 minus 16.8 to give you, what is that, 3.6? So that's going to end. And then to find the third standard deviation, you will take 70.8 plus 16.8 to give you 87.6. And you would take 3.6 minus 16.8, right? And you will get negative 13.2 to get the standard deviation. So what you have are standard deviation cutoff points. So if you ever hear someone that says, oh yeah, it's a standard deviation away, well, right? Now, what you can do is you can observe the IQ. The mean IQ is 100. That's the mean by the Princeton scale, with the standard deviation of 16. So if you are thinking about the IQs, you can take the online tests. Those are not real tests, but it will at least hint of the real thing. But I think the real test is like $200, $400, something like that, to do the real IQ test, to know where you fall. You can do the IQ test, and then standard deviation is 16. So that's and the mean is 100. So that means that the cutoff points are 100 as a mean, and then 116, 132, and then 148. Now, we said that 99.9, we'll have the exact numbers, but 99.96, I believe, percent of all data points fall within the first 3 standard deviations to the left and to the right. We actually had, in this particular example, 100% of data be in first 2, right? Because, oh, actually, no, I lied. Yeah, because this is 13. So we had 13 and 19 and 19 here, and then we had, I think, 50, maybe 9-ish and 62 or something. 62 only, right? So a lot of our data was really crammed in the first standard deviation. That tells you that is there a lot of variance and deviation in our data set? No, right? Because it's just right there, all in the pile. And but then when you look at IQs and you say, okay, 99.96 of the data points, that means people on the planet fall in the first 3 standard deviations to the left and to the right. Yeah, we have the IQs that are well below, 50, and we also have Stephen Hawking, who's clocking at 160, right, which is 4th standard deviation above the mean. And when you actually go and look at the proper use of word, imbecile, moron, and all of that kind of stuff, it's actually cutoff scores from the IQ test. Those are the official medical terms which we wrongly use in everyday language. I think, let me just see if I can find it real quick. So, IQ, range, let me see if I can do the IQ. So this particular chart has 15 as the standard deviation. Now, we'll actually come back to this and work with the bell-shaped graph and all of this kind of stuff, but IQ mean is 100, and then because the standard deviation is 15, the cutoff zone, the first standard deviation is the blue over here, and that's 100 to 115. Second standard deviation all the way to 30, and then 45. If you use the Princeton, I believe they go 16, which means 16, 32, 48. And the classification now, right, above 145, genius or near genius, 135 to 145, very superior, 115 through 30 superior, and then 85 to 115 is normal. So the mean average, so the first, right, but you see that 68% of people fall into the normal category. Now, 68 minus 100 leaves us with 32, which is 16% this way and 16% that way. So 16% of population are below normal, and 16% of the population are above what we call normal. So you can go and take the IQ test and see, you know, again, if you want the real thing, it costs a lot of money. $70 to $85. And then below 70, now it's called the borderline deficiency, but I think they have the actual in-depth charts. They have to have them somewhere. There we go. Took forever to find it. The Levine and Marx in the 1928 IQ chart, and they call it the precious, very superior, superior, bright, bright, average, dull, borderline, morons, imbeciles, and idiots. So that's the right. Now, this is what the actual chart is. These are the medical terms that we actually misuse and misrepresent. So anytime if I say one of these words in class, I truly believe that the IQ of the person I'm talking about falls in this range because of the actions they exhibit. I'm not trying to, you know, make, it's just, you know, it's scientific based, yes. Good. There we go. So it goes like Congress, and then, you know, regular stuff, and then we have research. Yeah. Anyway. So that's that part. And you see that the standard deviation plays a big role in understanding much of the everyday stuff that you deal with. Now, your project, you have data set. Hopefully you already started because, yeah, right? And you can now go and compute the standard deviation. Now, are you actually going to, let's say you have 100-point, right? It was annoying enough with 11 numbers. Imagine your data set is 100 or 150 or 250. Are you actually going to do this by hand? Hopefully not. You have the data in Excel, and you just create each one of these columns, and you assign the formulas to compute these things for you, so you don't have to deal with this Now you might be using Minitab or any other software to deal with this stuff quickly. So if you are in Excel and you have data 13, 19, 19, can anyone just go through the whole thing? Wait, 33?
51. Yeah, 33, 49.
Oh, 49, not 39. Okay, 49,
51.
51,
52.
52,
53.
62. So these are your xi's. And now what you're going to do here is you put equal, then you set this cell minus, and your mean was 37.2. And that will give you the number, and you just pick the corner and drag it down, right? Now, over here, you will be squaring that column. So you will say equal to start the function, this times, and then you push it again itself, right? That's the squaring. Now you can set one decimal space. You first set one decimal space, and then you drag this down. And it gives you all of the squares. You see how quick this goes. So if you have, it doesn't matter if you have 100 data set points, right? The first time typing in data, if it's not electronic, obviously will take much longer to type 150 than maybe 60 data points. But your project is much more valuable. I mean, mathematics being correct on 60 data points of 150 is the same grade. But the merit and the data set and everything is better if you have more data points. So clearly it was going to take longer to type these, but the rest is not going to take any longer to deal with once you have the data in. So now if I need to come up with the sum of all of these, I just push out the sum in the corner, and there is this 2812.6 divided by 10, and then divided by 10, and then take the square root, and you can do that on a calculator. So it's extremely quick to do these kind of things in the software. Now TI-83 calculators have a stat button, and you can do a lot of this standard deviation and everything else on the calculator, but again, you have statistical software like Minitab, and then obviously crowning above everything I mentioned, Mathematica, that does everything for you. All right, so that's that part. And now that you've seen the standard deviation, we said that larger variation brings larger standard deviation. And that's the way we understand this thing. So larger standard deviation is means more variance, more variation. Larger standard deviation means more variance in the data set. This is you understanding the concept. So mean doesn't measure everything. We need standard deviation to go with it. Yes?
When you say a larger standard deviation,
Larger number.
like how many of them there are?
No, larger number. So I said that, you know, the website we looked at had the IQ variation at 15, and Princeton had it at 16. So depending on which data, you know, which school of thought you want to use, but the standard deviation is that one number that you get, that we had, the 37.2 or whatever it was. Oh no, that was the mean, the 16.8. That's standard deviation, 16.8. So the larger the number is, the more variation to it. Now, there is another formula that you guys could use, and even, well, that formula has another form that you guys could use. So I'll just write here that as the other formula. And you know what? If you like the other formula better, go ahead. But it has more squaring, so I don't like it as much. So other formula says that S is equal to the square root of sum of all xi's squared minus sum of all xi's everything squared divided by n minus 1. As squaring twice. So, I don't know. Now what we can do is we can multiply by n to get rid of the double fraction. So this is the formula that book gives on page 110. And you can use it, but you can also multiply top and bottom by n, and if you do that, you will have the square root of n times summation of xi squared minus just summation of xi squared divided by n times n minus 1. So that's another form of the same formula. Again, use whatever you want. Let me make up another smaller data set to run these formulas one more time. How about 5 numbers? To go 7 numbers? Oh, the first number is 7. Thank you. What's the second number? 14 it is. What's the next number? Third?
22.
22 I heard? Okay, good. And what's the next number?
15.
Yeah, let's put them in order. So 75. And then what's the next number?
81.
81. All right. So these are the 5 numbers that we are going to work. And I'm going to do both formulas. So first the old formula. S equals square root of the summation of xi minus x mean, right, squared divided by n minus 1. Well, I need x bar for this one. And that's going to be when we add all of these. So 21, 43, 1, 8, 199. Is it 199 when you add all of this?
Yeah.
So 39.8 is the mean. And I set up my chart real quick. So xi is listed 7, 14, 22, 75, 81. And now xi minus 39.8. That's minus the mean. So I have 7 minus this is going to be negative 32.8. 7 minus this is going to be 25.8, negative 25.8. 22 minus this is negative 17.8. 75 minus 38, so that's like 75 minus 40, which is 35, so 34.2. And then plus 6 is 40.2. There we go. And now we're supposed to square these guys. Yes.
I believe that 75 minus 39 is 35.
35.2. And 41.2? Now we square each one of these. Then 75.8. 665.6. So close. 17.8 squared is 316.8. 35.2 squared is 1239. And 41.2 squared is 1697. We are going to add, hold on, 69.7.4. 69, no, 1697.4. Good. So now we're going to add all of these numbers. $4,994.16. Great. And now we have S equals square root of 4994.6 divided by 5 minus 1 is 4. So we are going to divide this number, 4994.6, by 4. We get that S is equal to the square root of 1248.65. And then we take the square root of that answer to get S equals 35.3. That's it. So standard deviation is 35.3. Do we see a lot of variation in the data? Sure we do, right? There's this big jump in data from 22 to 75. That's, right? It's a jump of 53. And the 53 is almost 2 standard deviations. So, yeah. Now what I want to do is I want to use the other formula for the same data, and I'm going to do that on a side as a comparison. Again, you can use whatever you like. I'm going to actually put the data in the middle because both sets use the same data. So now what I'm using is a different formula. S equals, and we have a summation of xi squared minus summation of xi's squared divided by n over n minus 1. We do not need mean, so that's a clear gain. We do not need to compute mean, but then you have 2 columns where you will be squaring. So, yeah. Let's take a look at our chart. I need my xi's, and that's 7, 14, 22, 75, and 81. I need xi squared. Well, I need to square each one of these numbers, right? So we have 49, 196, 484, 75 squared, 10 times 8, 5, 6, 25. And 81 squared is 6561. And then we have to add all of those values. And we have 12,915. And we are done with the first number. So I have S equals square root of, and I have over here 12,915. And that's going to be minus, and now we have to do the other side. So the other side says that I have to square the sum of the xi's. Well, it's easy to add xi's, right? 7 plus 21, so we know the sum. What was the sum? Oh, I didn't. So 81, that's 150. It was 199, right? So this is 199 divided by, 199 squared. 199 squared divided by n, which is 5, and then everything divided by 4. So that's, a little bit convoluted, but, such is life. So what is s equal to? Well, we have our number 199 squared, and we have to divide it by 5. So now I have square root of 12,915 minus 7,920.2, and everything needs to be divided by 4. So 12,915 minus the other number, and then you divide that by 4. So s equals the square root of 1248.7, which is the same as before, 35.3. Pick your poison, right? One of the exam questions on the 8th, because you picked to have the exam on 8th, will be compute standard deviation. And there is going to be, 4, 5, 6 data points at most. You all are supposed to have your calculators with you to, shovel through this data. So some questions will be as easy as what's the mode, right? And you look at the mode and you say, okay, mode is so and so. In our case, previous case was 19 because it was the only number that shows up twice with the largest frequency. So some questions are you just look at the question and you write a single number answer because you know the concept, you learn the words. But then on the other end of the spectrum, you have calculations that are intensive and crazy like this, right? So you can solve standard deviation questions using the formula number 1 or the formula number 2, whatever makes you sleep better at night.
You want to test us on both, right?
I'm just going to ask you to find standard deviation. I can't care less which method you use. We're all different, like snowflakes, right? But we only have 2 formulas, so I mean you can use also the this formula if you want. So you don't have the you don't have to divide by 5 like a double fraction. So this formula has no double fractions. It's not in the book. I just flipped it around to make it easier. All right. Then the statement which I said in words earlier, now we're going to write down the 3 standard deviations rule. It says almost all the observations in any data set lie within 3 standard deviations to either side of the mean. And we've seen that when we did our graph on the IQ. We've seen that Let me just switch to it again. So right here. So standard deviation 1, 2, 3. 1, 2, 3. So this where the blue ends. And look, 0.1% and 0.1% in the gray area outside. So that means 99.8%. 99.8% of data values are going to be within the 3 standard deviations. And that's pretty much almost all. In our cases, we had whatever we found, right, was there. But, you know, you really need to be an outlier in order to fall into these. Then they talk about use of technology, and that's it for this one. Now we're going to take a short break, and then when we come back, we are going to take a look at the last section. Well, I'm not sure if it's the last section. 3.4, which is the 5-number summary and box plots. Bye.